Hi, everybody. This is a hard solder alloy investigation team. Our project sponsor is Darren Jernay. We're with the Department of Material Science and Engineering. I'm Sam. I'm also joined here by Emma, Gus, and Drew. So a bit of our project background. Soldering applications are when you use high temperatures to melt two metals together. And for very high temperature applications, such as high temperature PCBs, certain alloys have to be designed to melt at these high temperatures and then not remelt when they get re-exposed to these high temperatures. So our project was based around designing one of these alloys for high temperature PCBs. So the current industry standard is 80% gold, which, as you can imagine, it's quite expensive at $66 a gram. So our project sponsor wanted us to hit about a 30% cost reduction, find a new alloy that could have similar thermal properties and similar electrical properties as the original material. So what that means is we'd have to have a melting temperature around 300 degrees, melting range of around less than 50 degrees, and we would want it to be fluxless for ease of integration into their industry workflows, which means that it would have to be greater than 50 weight percent noble metals, or gold in this case.
Our approach last semester was to focus on the research and development of the alloy as well as the system design. We did this by first establishing the project parameters, which enabled us to narrow down our literature searches to figure out, what's been done before and what elements are potential viable alternatives. We were able to test all of our hypotheses using thermocalc modeling, which outputs phase diagrams based on the composition of certain systems. And we were also able to model the solidification, which is important in telling us what it will look like after it's cooled. Focusing this semester, we wanted to do more of the actual hands-on and procuring the materials for these systems, so then we could cast them and characterize them and compare them to our modeling we had done in the fall semester. We were also able to hot roll to use case, which was important for our sponsor to ensure that they could actually use it in their processes. And then we were able to evaluate each of these systems based on the criteria from the initial project parameters.
So our main form of research was through thermocalc, and the main use of this was to model the solidus and liquidus temperatures to keep those around 300 degrees Celsius. So this example here, the system has a solidus temperature of 318 degrees Celsius and a liquidus temperature of 354 degrees Celsius. And then it meets that the range requirement of under 50 degrees Celsius as well. Then the other thing we used thermocalc for was Scheil solidification models. And what this shows you is the phases that appear as the solder system is cooled.
So we also attempted to model the conductivity of the alloy before we actually created it using a rule called the Nordheim rule. This is an approximation used for other similar alloys with solid solutioning. Now, when we did this, what we did is we took the Nordheim coefficients, we took tabulated values, and then we extrapolated values for unknown elements. And what we found is that there was a general trend, and that the Nordheim coefficient predicted patterns of conductivity across similar alloy systems, but it did not, however, have similar quantitative results. So we could use this as a reference point for comparing alloy to alloy, but we can't expect it to have what our approximations are going to actually have. So the simulations allowed us to identify three systems. One was gold, tin, zinc. Another was gold, tin, zinc, and silver. And the last one was gold, tin, zinc, and antimony. And these systems all had a 30% cost reduction. They all had greater than 50% gold. So they were fluxless. The melting temperatures were all around 300 degrees Celsius, and the melting ranges were all almost within 50 degrees Celsius. The antimony melting range being a little over 50 degrees Celsius was passed as fine with our sponsor. And we also saw that they predictably had similar conductivities to the original gold tin standard.
After we identified these systems, we purchased the materials to then cast them in the melt spinner using induction heating. And just as our models predicted for solidification, we air cooled them down to the size of about 20 millimeter size gumdrop castings. We then used these to characterize. We used backscattered secondary electron imaging to ensure that our matrix had homogenized and that we did in fact have the composition that we targeted, which here the example is the 80-20 gold tin control system, in which we were right around our target weight percent. Using this, we were able to ensure that we had the correct melting temperature, which was of concern to our sponsor. So here we had predicted a 300 degrees Celsius melting temperature for the gold tin standard, and we were within 1 degree of that. We also fell within our desired melting range, and we measured the onset of the melting temperature peak so that we could process these using hot rolls to mimic the use case scenario.
So for hot rolling, we used the melting temperatures that we just received through DSC, and we heated the gold tin system and the gold tin antimony zinc system to 15 degrees below their onset. And then we rolled them using heated hand rolls. And then we also used some pennies to kind of gauge the strain rate we were going at, because there was not a strain gauge on the rolls. However, the samples experienced brittle failure before we were able to achieve the desired strain rate. The control system failed at 30% strain, and the antimony zinc system failed just below 2% strain. And this was to determine the any difference between the as cast and the as rolled conductivity of the samples. The main reason for the brittle failure was due to the significant amount of intermetallics, and then there was also significant amounts of casting porosity within the systems. As you can see in the scanning electron images, there are lots of tiny pores within the sample, which act as stress concentrators. And then there are also significantly more non-cubic phases than cubic phases. Cubic phases tend to be more ductile and easy to work with compared to non-cubic phases. So in conclusion, the alloys that we cast did hit the cost reduction. They were all fluxless. They did meet the melting temperature requirements while still having the narrow melting range. And they experienced similar conductivity to our control sample. They just didn't have the mechanical properties present that we were looking for. So our recommendation moving forward would be to try to increase the mole fraction of cubic materials to try to determine more alloys that would be easily workable and not have so many intermetallics, which you could evaluate different solidification models and new systems. And then another thing to do would be to minimize the shrink porosity during the casting process by altering the casting conditions so that the sample would avoid having those stress concentrators. Acknowledgements. Thank you, Dr. David Labyak, for being the AME faculty advisor. And thank you, Darren Jernay, for this project.